Okay, Assalamualaikum. Morning. Can you hear me? Okay, that's good. Right, apa khabar semua hari ni? Sihat? Alhamdulillah. Dah breakfast? Jom, ada lagi yang tengah joining now. Belum breakfast eh? Alhamdulillah. Okay. Okay. Um, okay, let's get started. Okay, let me share with you the content. Right. Hold on. I cannot approve from here. uh, okay, all right. Okay. That's one. Let me share the PVC-ROM page. Where is it? Mm, Screen one. This one is where is it? Can you please confirm whether you see the PVC-ROM page? Oh no. All right. Okay, hold on here. Mm, okay, now can you see the page? PVC-ROM page? All right, that's good. Okay. Do you also see? Hold on, I do not know why I have to quit sharing to be able to approve students joining. Usually they are just Come on, give me a while. Three. Okay, so let me. Okay. All right. Ah, another one. Oh, okay. This one is okay. I don't have to close. All right. Okay, let's continue. So on today's what, Wednesday, right? So on Monday we have discussed up to the introduction of calculation of carrier densities into quasi-neutral region. So we finish at depletion region calculation, where you already learn how to calculate minority carrier densities at the end of depletion region on A side and B side, or on P side or N side, right? P side or N side at 2 points, right? Point A and point B. So after we now know what is the concentration of both minority carriers, now we are trying to extend. We're trying to extend to calculate their carrier densities in the quasi-neutral region. Okay, in the quasi-neutral region. So if you look at this slide, so you can see here this whole thing on the right hand side. Let me just zoom in. Oh, the page is blank, really? Oh, okay. Oh, it shows here that I'm sharing two pages. Okay, you don't see anything. Let me reshare. Okay, let me redo it. Okay. Okay, let me share the PowerPoint first. Okay, can you see the PowerPoint now? Nampak tak slide? Okay, nampak? Okay, right. I don't know why you can't see it now. It was also shared. All right. Anyway, let's proceed. Right, can still see, right? Okay, good. Okay, so all right, we have discussed up to the introduction of minority carrier calculation into the quasi-neutral region, right? Quasi-neutral region. So you can see now on the you can see now on this slide. So we're trying to calculate the minority carrier densities into the quasi-neutral region on N side. So this can only be done provided if you know the minority carrier density at the end of the depletion region on the right hand side, on the B side. Okay. Hold on, we have another student joining. I cannot approve it here. Okay, right. Can see, right? Can see the slide, right? Okay, right, good. So now let's move on to to the next one, right? We're gonna continue with this slide actually. Okay, so we want to calculate the density of minority carriers on both sides in these two regions, right? On the left hand side, here, left hand side, and also to the right hand side. Okay, so the central region here is the depletion region or space charge region. So you've done your calculation there because previously you have calculated the minority carrier densities here, right? So previously we've done this curve. Let me draw again. We've done that curve. Okay, due to the diffusion, you've calculated this point. So now we're going to use this point P and B as your starting point to know the minority carrier densities in the quasi-neutral region, right? So that'll be a starting point. So the same goes to minority electrons, right? The same goes to minority electrons, where we have already looked at this curve, and now we want to use the NPA as your starting point um, in order for you to know the minority carrier densities in the quasi-neutral region as well, right? So we're going to look at the equation here given here, P and X and NPX, right? P and X will be the minority carrier whole, minority whole as the minority carrier in N region, and we're gonna also look at NPX, which is a minority carrier electron in P region. Okay, so this can be what we call it's quite a long derivation actually. I'm going to show you before I come back to this page. Let me just show you the PVC ROM page. Okay, so can you see the PVC ROM page now? Wait a minute. Okay, so if you want to know the derivation of this step, I want you to go through this solving for quasi-neutral region, which is here. You can come down here to section 3.6. Okay, section 3.6, section 3.6 on PV-CD-ROM. Okay, so you can have a look at this section, and then it's going to show you the long derivation on how do you actually get the general solution. Okay, general solution. So on my slide, I just summarize the finding. Okay, so I'm going to come back to this page. Okay, so we have last time covered briefly on continuity equation, and to be able to solve the quasi-neutral region minority carrier densities, we have to revisit the continuity equation. So this can be given by the G minus U, where G is the generation rate of excess holes. Remember, this is n-type region. Okay, so n-type region is on the right, so we're trying to look at the right region now. So the continuity equation for this particular case is given by G minus U, So where U is the net recombination rate of excess holes. So in this case, hole is the minority carrier, right? Hole on the right hand side, hole is the minority. Hole is the minority. Minority. So and G is the generation rate of excess holes. So in this case, we are not talking about any. Oh, sorry. We're not talking about uh, illuminated illuminated case. So G is 0. There's no new generation. There's no new generation. So whatever you have on the right hand side, minority carry hole is actually from the diffusion process from n-type p-type region. Sorry. Okay. So if you look at this U net generation rate of excess holes, that will be given by delta P over tau H, right? Delta P over tau H. Oops. So that will be given by Pn minus Pn naught over tau H. So delta P is Pn minus Pn naught. So the minority carrier hole in n-type minus minority carrier holes in n-type as well at thermal equilibrium. So you'll see the difference then over the tau H, right? The lifetime. So this will be given by the same equation here. And then if you look at the derivation on section 3.6, you'll find out that this will be given by a general solution down here. Okay. Nanti try tengok dekat derivation for you to understand the whole process. This is a summary of the process. Okay, so in this general solution, you have to know that the diffusion length of holes, if you're talking about silicon, you have a silicon here. For example, your silicon is 200 or 300 micron maybe. So your diffusion length is given by square root of the tau, right? The tau diffusivity times lifetime. So if you're talking about silicon, that's typically in the region of it can range from 1 micron up to 1000 micron. So if your thickness is 300 micron in this case, what is your minimum diffusion length that you want? Berapa minimum diffusion length that you want to have to be able to get a good device? Anyone? How long do you want your carriers to diffuse? Berapa minimum? Anybody? Okay, let me look at your name. 1 micron. Okay, I say 1 micron. Any other answers? 1 nano. But remember the diffusion length is what? What's diffusion length? The average distance traveled by the carriers from generation to recombination, right? You want them to travel as short as possible or as long as possible. Dia nak dia travel jauh ke travel dekat? As long as possible, right? Yes, correct. So we want the carriers to travel as long as possible. So in this case, if the thickness of silicon is about 300 micron, oops, sorry. If the thickness of the silicon is about 300 micron, how long do you want the carriers to travel? Katalah ni you ada contact on the front side and also on the rear side. Let me draw. Metal contact. You're going to learn this one later on. but assuming this one is metal contact for them to go out of the device. So you want them to cross as you want them to get to the contact, right? So we want them to travel as long as possible. So in this case, we want the diffusion length of the carriers, in fact on both sides, P side and N side, to exceed, to be more than 300 micron. So kita nak dia punya diffusion length to be more than 300 micron. Kalau tidak, dia tak sampai. So assuming, katalah even though your PN junction is, we're gonna see it in the next, I think in the next topic, or towards the end of this topic, sorry, we're gonna see that you're gonna form a PN junction on the front side, and we have discussed that typically the junction is 1 micron or less. For some reason, we'll see that. So if your, katalah kat depan ni N type, belakang ni P type, so try to relate to this curve on the right, okay? Katalah you punya electrons from N side ni diffuse into P side, they diffuse di cross junction kan? So the cross junction, so that's only about 1 micron from the surface, right? So dia masih ada how long to go into through the silicon to get to the rear metal contact. Berapa jauh lagi dia ada untuk dia travel? So the thickness is 300 micron, and the junction is very close to the surface. It's only 1 micron deep, for example. So the moment the electrons from N-type diffuses through the depletion region into the P-type region, which is quasi-neutral region that we are discussing now. So the electrons have to travel through at least 299 micron, right? 299 micron to be able to get to the metal contact. Baru dia disampai ke metal contact, then only it can be extracted. Kalau tak sampai kat metal contact, that means it's going to recombine and you're not going to get your results on the measurement, right? So therefore, you want the diffusion length of your electrons in this case to be as long as possible. So the same goes to hole. It's just that hole, kalau your junction design is something like this and is very close to the surface, so you punya hole kat sini is only 1 micron from the surface. So maybe the hole doesn't have to travel as long to be able to get to the metal contact. So that means, bottom line, we want both carriers to reach the metal contacts to be able to get our device to be working, right? So the movement of the carriers, or the density of the carriers, is given by this equation, by Pnx for hole, npx for electron. Okay, so one question. Sekarang kita discuss about having a junction on the front side of the device, for example. So is it possible for us to have a junction at the back of the device? So what do you think? Let me sketch something here. Okay, no, hold on. Okay, so let me draw something here. Let's say this is your silicon, 300 micron, maybe 300 micron. So far we have discussed on having a junction on the front hand side, at this side front. Can we also have a junction at the back? Or maybe we don't have any junction at the front, but just have a junction at the back. Will it also work? Any ideas? Maksudnya junction kita tak letak kat depan, tapi we have a PN junction at the back of the silicon. Is it also possible? Any idea? Who's here? Right, Faika, what do you think? Faika, what do you think? Maybe yes. Okay, Faika said yes, maybe yes. All right. Who else? Any other ideas? Is it possible to have a junction at the back instead of at the front? By Aniza. Tak pernah panggil Aniza ya. Aniza, what do you think? Boleh tak buat PN junction at the back of the device? Tak kisahlah silicon ke, gallium arsenide ke, cadmium telluride ke. In principle, can we have a junction at the back? Any guess? Syazwani? Oh, Syazwani tak ada balik kampung kot. Oh, Syazwani is here. Oh, Shamim, what do you think? Can we have a junction at the back? Shamim? Or any other guess? Somebody else? No idea? Right, the answer is correct, Faika. We can also have a junction at the back. Right? So, nanti kita akan tengok dalam semiconductor device. When you want to design a PN junction, it's very, very flexible. So you can either have a junction, your junction on the front end side. You can also have your junction at the back. You can also have your junction in PIN, just like your test one question, right? You can also have, multiple designs. So it really boils down to what do you want to have in your devices, right? So it's not necessarily on the front end side. In fact, you can also have a junction on the front side and at the same time having another junction at the back. So you can also have a double junction, right? So now we're talking about PN junction. What if you have a silicon wafer with doping level of 10 to the 16 and you diffuse a layer on top of the P wafer to be P plus. Let's say you have a P silicon wafer, P plus, P 10 to the 16, and then you provide a layer or you dope a layer on top of the silicon 10 to the 18, and that's P plus. Do we also call it as a junction? What do you think? If you have a P wafer and then you dope a P plus, do you call it a junction as well? Any guess? Yes or no? What do you think? No ideas? Farah, what do you think, Farah? Boleh tulis kat chat box. Yeah, Jasmine, correct. It's called P. You can call it as P plus junction, right? It's also a form of junction. So, sekarang ni kita belajar just a basic concept je, PN junction. It can also be PN plus junction. It can also be P plus junction. It can also be N plus junction. So the idea is that the moment you have a difference in doping level, you're gonna have a junction. Cumanya the basic is kita belajar paling basic lah, paling foundation is PN junction lah, because the junction is formed based on opposite polarities, right? Electron and hole. Tapi you may also have P plus, N plus, or n plus plus junction in real devices. Okay, back to this. The minority carrier density in your quasi-neutral region on the n side, which is on the right, will be given by will be given by p and x, and your minority carrier on the left will be given by npx, right? Okay, Aniza, no problem. All right, so now let's go to the next page. So okay, so I want you to not to worry about the general solution, because I want you to have a look at the derivation in PV-CD-ROM that I've shown you just now. So this will be the general solution, right? This will be the general solution that you have to look at. After applying boundary condition in this general solution, you will be able to you'll come to this point where the p and x on the right hand side in the quasi-neutral region in n-type will be given by p n naught plus p n naught exponential of qv over kt minus 1 times exponential of minus x over LH, right? LH is the diffusion length of the hole in n-type on the right hand side. Okay, so right hand side, so that's the first one. So on the left hand side, so the calculation will be given by npx prime, if you like, prime. So that's given by np naught that you have calculated at thermal equilibrium plus np naught times EQVKT and the same equation, right? Except it's on the left hand side. So this will give you a minority carrier densities in forward bias condition in the opposite region. Okay, in the opposite region of the junction. So we'll do some calculation towards the end of this lecture note. Today, what time is it now? Oh, 9:35 already. So now we are in quasi-neutral region. If you look at that statement, new slide. So in the quasi-neutral region, the majority carrier concentration must have a corresponding change in their concentration in order to maintain space charge neutrality. This is the key point. So if you look at this below a diagram, the left hand side and the right hand side are actually the same curve, but the left hand side is linear, but the right hand side is semi-log, right? This one is lon on the right hand side and this one is linear. Selalunya kita guna yang lon base lah. Usually we use this for explanation, right? So in fact, all the previous explanations we use the lon base, semi-log base, right? So you can see a straight straight concentration, relatively flat concentration in quasi-neutral region on both sides, P and N, and a drop in profile in the depletion region. Okay, Pn ni yang kita pakai ya. So this is the quasi-neutral region. So right, we're gonna come to a concept where we're gonna treat this equation by two conditions, right? So we're gonna have two conditions. We're gonna have a thick diode and a thin diode. Okay, so the first one we call it thick diode yang tebal. So the second one we call it thin diode, right? Thin diode. This one of the second one. Right, apa beza thick diode and thin diode? Thick diode is where you have a very thick PN junction in total. So that means your minority carriers that you have calculated so far, PNX and PX, will recombine before they reach the end of the silicon, right? So that means if you plot here, if you draw here silicon, so that means the carrier doesn't manage to get to to the end of the silicon to get to the contact. Dia tak sampai sebab apa dia tak sampai? Sebab dia punya distance to travel is too long, and the diffusion length for thick diode, the diffusion length is less than the device thickness, right? The diffusion length is less than the device thickness, so therefore you call it thick diode. Okay, whereas for thin diode is where you have your diffusion length more than the device thickness, right? So that means you punya PN junction, the whole thing, the whole silicon, the thickness of the whole silicon is less than the diffusion length of the carriers. So that means carrier boleh sampai ke device, right? Boleh sampai ke metal contact. So we have two conditions, remember, thick diode and thin diode. So this slide is for thick diode, right? Thick diode. So we're going to come to thin diode a little bit later. So for thick diode, minority carrier current can be calculated from the above distribution, from previous distribution. So on N side, this will be the equation. N side, this will be the equation. JH will be the equation. And on P side, JE here will be the equation. Right. So if you look at this equation, is it based on drift or diffusion? If you look at the equation, is it based on drift or diffusion? Anyone? Diffusion, right? Yes, as a result, diffusion, right? So it's diffusion. So you have QD dPdx, QD dNdx, right? Negative for the dPdx, right? Yeah, I got it. It's okay. So it's based on diffusion. Kenapa diffusion? Why is it diffusion? Why is it not drift? Kenapa diffusion? Why there's no drift component? Because the moment you applied your forward bias and you force the carriers to cross again the depletion region, they will diffuse across the depletion region, right? So therefore you're going to have diffusion current. So you can revisit balik our previous lecture where the main contribution will be diffusion, right? So therefore the current related to the minority carrier densities on both sides of P and N are based on diffusion, right? Based on diffusion. So JH will be given by this equation and JE will be given by second equation, right? So you have to plug in all the important parameters like diffusivity, NP naught, diffusion length, voltage, and then what else? Diffusion length, right? Diffusion length is given already. So this current, the JH and JE, will appear as this on the right hand side curve. Okay, so this will be the minority carrier currents in forward bias junction, PN junction, right? So JH will be in this shape more or less. If you try to calculate at every point, and JE will be like that, right? So in order for you to get the total current, you have to plus JH and JE. JH plus JE, right? Okay, thick diode still. So this is actually the shape of your of your diffusion current densities that you have just calculated, right? So typically, if you look at this schematic, so the W part is the depletion region, and the device thickness is typically around 200 micron, 300 micron. It really depends on what type of devices are you fabricating, right? So the width of the depletion region is typically in the order of 1 micron or less, just like the calculation that we did last time when we calculated the depletion region width, right? So from the calculation we got it about 0.95 micron. So it's typically in the region of 1 micron or less. So the device thickness in this case is about 200 micron. So that means you have your silicon here, silicon here to be 200 micron, more or less. Then assuming this is your PN junction, the depletion width there is only about 1 micron. It's only about 1 micron, okay? So kalau you plot like this for P and N, so it's gonna look like this. You just have to flip, right? Flip this one into horizontal representation. So JH is diffusion current density due to minority hole in N type, and JE is the minority carrier electron in P type, right? Minority carrier electron in P type. So the profiles are pretty much like that, but we don't know whether JH is higher than or lower than JE. Ni cuma contoh je. So whether JH and JE is higher or lower than uh, the other one, we don't know unless we do the calculation, unless we know the doping level and the diffusion length and stuff, right? So ni contoh je. Ni tak semestinya um tak semestinya bermaksud JH is always higher than JE. No, it's just an example, right? Just an example. It depends on your parameters that you have to plug in, and you have to see for yourself what's the value, right? So assume that because depletion region is small, no change current across the depletion region. So is the change of current in depletion region is almost negligible. So there is a small change, but very very small. So we approximate the change in current as close to zero, right? Because we are now more interested into the minority carrier currents in the quasi-neutral region, right? Quasi-neutral region on both N side and P side. And we also assume that there is no recombination in the depletion region for simplicity. But in actual case, later on we'll see when we discuss about diode equation, when you have your actual devices fabricated, you will always have a recombination in the depletion region. But for fundamental calculation, for establishing the equation simplicity, we have to make some assumptions, and these include assuming no recombination in the depletion region. Okay, so I think I'll just stop here. All right, okay, let's go for the other slide, last one. Right, from this slide we have discussed just now that in order for you to get the total current, you have to know the current due to hole and the diffusion current density due to electron as well. So you have to plus both of them. Okay. So this will be pretty much summarized by the first row of the equation there. J total equal to J diffusion current density due to electrons plus diffusion current density due to hole. So, and that will be given by this. Okay. Q n p naught d over L plus Q p n naught d over L times exponential component. And then this equation can be summarized as this. So J will be equal to J naught exponential QV over KT minus 1, right? And notice that the moment you summarize this equation into J equals to J naught, J naught will actually be equal to this component, right? J naught will be equal to Q d over L n squared over NA plus the same thing for whole, right? So J naught is that. So what is J naught? Last time we have discussed that J naught is equal to leakage current, leakage J naught, J naught. So it's also called diode saturation current density. J naught is also called saturation current density. Right. Note that J naught is small for large diffusion length. If you look at this equation, to be able to get low J naught, you have to have large diffusion length, which is large LE or LH. right? Large diffusion length and also large doping level. So you also need to have large Na or Nd on both sides to be able to get low J naught. And for a large band gap, as well, if you have a large band gap, it typically will result in small Ni. So J naught is the most important diode parameter. So in a diode, we'll see in the lecture tomorrow, we're going to look at a diode equation. So which is essentially this equation. We're going to discuss about this equation tomorrow. So J is equal to J naught exponential QV over KT minus 1. So J naught is the leakage current or diode saturation current density. And in fabricating your semiconductor devices based on PN junction, we want our J naught to be as small as possible. Kita tak nak J naught too tinggi ya. When your J naught is high, that means you have high leakage in your device and that's very bad. So kalau you ada leakage, apa maksudnya? Kalau you ada leakage, that means if you want to switch off your device, but then the leakage current is too high, you may end up switching on the device, right? So kalau you nak switch off the device, tapi if the leakage current is too high, you might end up switching on the device, still turning on the device. Sebab sentiasa ada current yang flowing through even though you want your switch to turn off, right? So that's why you want your saturation current density or leakage current to be as small as possible. So it's typically in the order of 10 to the 12, lebih kurang J naught. So if you have your J naught to be in the region of 10 to the 9, 10 to the 8, 10 to the 5, 10 to the 6, so your device will be in trouble. So we want to be in this region, right? 10 to the 12, 10 to the 13 ampere per cm squared, right? Ampere per cm squared, saturation current density. So to be able to get that, that means if you're trying to design a semiconductor device, so you need to use parameters which will produce large diffusion length, large doping levels, and hopefully large band gap as well, to be able to suppress J naught from your design. Okay, certain J naught, certain condition you can suppress from the design itself. That means bukan you fabricate baru tengok J naught. You can design your device before you fabricate to be able to design your expected J naught, and eventually you can see what do you actually get in your final devices, right? So I'm just going to stop at this point. So we're going to continue on with the rest of the pages. Yep, we're going to look at diode equation and then a thin diode for tomorrow. Yeah, I think that's it for today. Any equation, but any questions for today? Anything? So hari ini kita dah cover up to quasi-neutral region. So test 2 ada calculation tak? Test 2 I haven't decided, but more or less it will be something like test 1, right? Kalau ada pun maybe, I don't know, maybe not that simple lah. Kalau ada pun, maybe not that simple. I haven't decided yet. Sebab the concept will be open book still. So I'll think about it. Okay. Hari ni saya tak sempat nak brief to you about the presentation. So I'll probably upload your presentation task on Elearn sometime today or tomorrow. But let me give you an idea first before we stop. They're all together 33 of you, so we're gonna have individual presentation, but secara maya lah, sebab kita tak ada kelas kan, tak ada face-to-face class. So I'll give detailed instruction later on, but some ideas to you. You will be assigned to work on some materials related to some semiconductor device. So that means one will get one. So you may get different devices than your friends. Then you'll be requested to do a 10-minute presentation, totally depending on you. I'll give you the rubric for assessment, apa yang akan saya assess on e-learn later on. So you'll be doing your 10-minute presentation recorded. That means you're going to record yourself on a video, and then you will upload your presentation video on Padlet. So have you ever worked on Padlet before? Pernah guna Padlet tak? Alright, okay, pernah guna. Oh, ada yang tak pernah guna So Padlet is just it's just a website for you to upload your stuff, right? Your file or whatever, right? So we'll probably upload on Padlet. I haven't decided. Probably on Flipgrid, right? Maybe. I'll see first and I'll let you know. So you will do your presentation up to 10 minutes based on your assigned devices, and then you akan upload you punya presentation on either Flipgrid ke maybe Padlet. Then during the you're gonna be given 2 weeks. So after the 2 weeks, so we're gonna play selected videos in our class. So each video will cost you about 10 minutes. It will cost us all about 10 minutes. So I'm gonna play the video for 10 minutes, and then there'll be a Q&A session to the person who work on those devices. Contoh, katalah saya assign Hazika, Aniza, Shamim, I don't know, maybe Jasmine, and Asrizal maybe. Katalah you are assigned to work on BJT, bipolar junction transistor. So each of you has to prepare a presentation video, you presenting with whatever skill that you want to use, the material that you want to use to present about BJT. So nanti you akan upload you punya file on either Flipgrid ke Padlet ke. Then we're gonna play selected video presentation on BJT. Then all the 5 of you will be asked questions on our WebEx class. Okay? So dia macam presentation dalam kelas yang ada Q&A session, except the presentation will be done through your videos, and we're going to play some videos. Then questions will be asked to the 5 of you, right? The question can be from your friends who can ask online on WebEx, and can also be from me, right? So the whole thing will contribute to your presentation mark, which is 20% of your whole mark for this course. All right? Nanti saya akan put this into details. I've outlined a little bit, but it's not finished yet. So probably today or tomorrow, I'll put it on e-learn, and then I'll tell you again. Okay? So basically, for the second part, when we learn about devices, you will be the content creator of the course. So that means you're going to learn BJT from your content. You're going to learn solar cell or JFET or lasers from your own content. So that means you're going to create your own content, then you're going to share your own content in your presentation, and then we're going to discuss and have some Q&A session, and then we're going to learn from your own presentation material, right? Okay, is it clear so far? Alright, okay, clear. Okay, that's good. Nanti saya akan bagi the detailed instruction on e-learn, and then I'll see. So you are given sometimes 2 weeks. Hari ni hari apa? Hari Rabu kan? So I'm thinking of sekarang week 10, right? Yeah, Jasmine is 20%. So 20% for your presentation 1, and we're going to have another presentation before we end the course. That'll be another 20%. So that means so far, as I said on Monday, you have finished 20% from your assignment 1, 20% from your test 1, 40 lah kan. 20% from your presentation 1, 60%, 20% from your presentation 2, and 20% from your test 2. So altogether 100%. So hari ni Rabu, so I'll probably give you today or tomorrow, and then it will be due in the next 2 weeks. So that means sekarang week 10 kan? So week 11 next week, week 12. Yeah, it's gonna due sometime week 12, Friday, 5 p.m. for you to upload all your videos on the platform that I'm gonna decide later on, right? So week 13, we're gonna start playing your presentation, and then we're gonna do the Q&A session for your presentation 1 session, and then you're gonna be marked based on that, right? Then done 20%. Okay. So no questions so far. Okay. All right then. If nothing else, then yeah, that's it for today. So we're gonna continue with Q&R tomorrow, and hopefully we can finish the PN junction biased, and the next one will be PN junction under illumination. Okay then. See you all. Bye bye. Assalamualaikum. Stay safe.